Large language models have transformed the landscape of artificial intelligence. But as they grow in size, so do their computational demands, making efficient inference a critical challenge for real-world deployment. Today, we dive deep into a groundbreaking new method called IG-Pruning, input-guided block pruning for large language models, a technique that dynamically adapts pruning decisions based on input content, delivering superior performance with minimal overhead. Let's unpack what makes this approach so powerful. The problem: static pruning isn't enough. Traditional pruning methods reduce model size by removing entire transformer layers, what's known as depth pruning. These approaches are effective, but they rely on a fixed pruning mask determined once, offline, based on global layer importance. Here's the catch: different inputs, like a scientific question, a casual chat, or a legal document, require different computational pathways. Yet static pruning forces all inputs through the same fixed structure. As a result, even if two pruning masks have the same sparsity level and similar perplexity scores, their performance across downstream tasks can vary wildly. One might excel at reasoning, while another fails on common-sense tasks. That's a fundamental flaw. Existing dynamic routing methods try to fix this, but most operate at the token level, making skip decisions per token. This introduces serious drawbacks: poor understanding of sentence-level semantics, inconsistent routing, and heavy computational costs from training complex router networks. We need something better. Introducing IG-Pruning, dynamic input-aware efficient. IG-Pruning solves this by introducing input-guided blockwise pruning, a two-stage framework that discovers diverse, high-quality pruning masks during a lightweight pre-training phase, then selects the best one at inference time, based solely on the input's semantic content. No retraining. No extra parameters. Just smarter, adaptive computation. Let's break it down. Stage 1, discovering smart mask candidates. The first stage is all about mask discovery, finding a set of high-performing pruning masks that cover a wide range of input patterns. Instead of training one fixed mask, we cluster inputs by semantic meaning using a sentence encoder. We feed calibration data, like high-quality synthetic text from FineWebEdu, into a model to generate embeddings. Then we apply k-means clustering to group similar inputs into semantic clusters. For example, one cluster might contain scientific questions, another legal documents, and another casual conversations. For each cluster, we train a dedicated layer mask using hard concrete distribution, a technique that enables continuous, differentiable mask learning with L0 regularization. This means we can optimize the mask as a soft, continuous value between 0 and 1 during training, then binarize it to 0, skip, or 1, execute at inference. The key innovation: we apply Lagrangian sparsity constraints to enforce a target pruning rate, say 25% sparsity, while still allowing the model to explore diverse pruning patterns across clusters. And here's the beauty: only the mask parameters are trained. The original model weights remain frozen. This keeps training fast, lightweight, and memory efficient, able to run on a single consumer GPU. Stage 2, dynamic routing at inference. Now comes the magic: dynamic routing. At inference time, when a new input arrives, we encode it into a semantic embedding and compute its distance to each cluster center. We then select the most semantically similar cluster and apply its pre-trained mask. No router network. No additional training. Just a simple, efficient distance calculation. But what about autoregressive generation? Can we skip layers without breaking the key-value cache? Yes, and here's how. For feed-forward FFN blocks, if the mask says skip, we skip the entire FFN computation. For attention blocks, we can't fully skip the computation, because we still need to maintain the key-value cache for autoregressive generation. So we do something clever. We compute the key and value projections to preserve cache state, but skip the expensive scaled dot product attention operation, the most computationally intensive part. This selective computation preserves the model's ability to generate coherent text while slashing compute. Why it works so well? Let's look at the results. On Llama 3 8B at 25% sparsity, IG-Pruning achieves 87.18% of dense model performance, a full 10.86 percentage points better than the best static baseline. On Qwen 3-8B at 13.9% sparsity, it maintains 96.01% of dense performance, outperforming the next best method by nearly 6 percentage points. And it's not just about accuracy. The method is extremely efficient. Training all 16 masks takes under 15 minutes on 4 H800 GPUs, and only 1 hour even at 37.5% sparsity. And because we're only training mask parameters, it runs successfully on a single RTX 3090. Even more impressive, the block-level pruning strategy, where we prune attention and FFN layers independently, outperforms layer-level pruning by a wide margin, especially around 20% sparsity. Why? Because it gives the model greater flexibility. Attention layers in the middle of the network are often redundant due to residual connections, so pruning them saves compute without hurting performance. Meanwhile, FFN layers tend to retain more critical information, so they're preserved more often. Visualizations of the masks confirm this. In Llama 3, attention blocks are heavily pruned in the middle, while FFN blocks remain intact. In Qwen, the pattern is more balanced, showing how different architectures adapt their pruning strategies. What makes IG-Pruning unique? 1. Input adaptive computation. Unlike static pruning, IG-pruning tailors the computational path to the input's semantic content, ensuring optimal performance across diverse tasks. 2. Efficient training. Only masked parameters are trained. Model weights stay frozen. No retraining, no memory explosion. 3. Negligible inference overhead. The routing mechanism is just a nearest neighbor lookup. No complex networks. No latency. 4. Flexible pruning granularity. Blockwise pruning allows independent treatment of attention and FFN components, offering fine-grained control over efficiency and accuracy. Key insights from ablation studies. We tested the impact of different variables and found some surprising truths. More clusters equals better performance. Using 16 clusters, instead of 4, boosted performance by over 10 percentage points at high sparsity. More clusters mean more specialized pruning paths. Calibration data matters. Using FineWebEdu, a diverse, high-quality pre-training dataset yielded the best results. In contrast, using Wikitext 2, the standard calibration set for baselines led to a noticeable drop in performance. But here's the kicker. Our method still outperformed the baseline even when using Wikitext 2. That proves the gains come from the dynamic routing mechanism, not just better data. Limitations and future work. Of course, no method is perfect. Performance depends on clustering quality. If clusters aren't well separated, the routing fails. And the method is sensitive to hyperparameters like L0 regularization, Lagrangian terms, and cluster count. We also didn't test its impact on factual accuracy. Removing layers could weaken the model's ability to recall facts, increasing the risk of hallucinations. But this opens a promising future direction, combining IG-pruning with hallucination mitigation techniques. For example, integrating methods like TruthX, which edits internal representations to improve truthfulness, or truth-aware context selection, which filters misleading inputs, could yield models that are not only efficient but also more reliable. Final thoughts. IG-pruning isn't just another pruning method. It's a paradigm shift. By making pruning input-aware, it moves beyond one-size-fits-all compression. It enables LLMs to think before they compute, selecting the most appropriate computational path for each input. This is the future of efficient AI, models that are not just smaller but smarter. For researchers, it offers a new way to balance performance and efficiency. For deployers, it unlocks the possibility of running powerful LLMs on edge devices, mobile phones, or even real-time applications. If you're working on model compression, inference optimization, or efficient AI deployment, this paper is a must-read. And if you want to try it yourself, the code is available on GitHub. Thanks for watching. If you found this deep dive valuable, hit like, subscribe, and share. Stay curious, stay informed, and until next time, keep pushing the boundaries of what AI can do.